Today's session is an introduction to SN1 SN2 E1 E2 reactions. It is one of the most difficult topics in organic chemistry. The only one more difficult, in my opinion, is the only topic more difficult than substitution elimination is spectroscopy. But when it comes to reactions, too many students try to memorize flowcharts, and let me know in the comments if that's been the situation with you, where you memorize a flowchart to know which reaction, and then if something doesn't look right, you just completely get confused and you don't know what to do. The problem is you cannot memorize. You have to understand. You have to know what is happening and why, so that when you see something bigger, something scarier, you know exactly what to do. And so if you are ready to understand these reactions to the point where you don't even need a flowchart, I want to see fire emojis in the comments, because we are going to take it all the way back to basics today and make sure the information is crystal clear. Starting with the SN2 reaction. SN2, the S stands for substitution. N is nucleophilic, and I'm writing it shorthand. The 2 does not tell me how many steps. Be very, very careful. The 2 tells me how many molecules are reacting at the same time in the rate determining step. It is a bimolecular reactions, 2 things colliding at the same time. The way this reaction works is we'll start with something very simple. In this case, we'll take a secondary alkyl halide. What we're looking at here is the alpha carbon. That is the one holding the leaving group. This is where the attack will happen. Bromine is a highly electronegative atom. This is my leaving group. And even though it has a covalent bond that it is sharing with the alpha carbon, the electronegativity of bromine makes it greedy, and it starts pulling and pulling on the bond between itself and carbon. That makes this carbon very partially positive and the bromine very partially negative. So partially positive that if I bring a molecule nearby, specifically a molecule that is highly electronegative or straight up negative, like an OH minus, which we'll use in this case, that negative oxygen is attracted to the partially positive carbon and attacks. When it does so, when it attacks, it'll form a bond between itself and carbon, which would give carbon too many bonds, because don't forget, I also have a hydrogen atom, which is invisible in line structure, but it is definitely still there. When oxygen attacks, carbon is going to have to break something so it doesn't have 5 bonds. And specifically, what'll break is the bond between itself and the leaving group, because bromine was already pulling so much, trying to pull the electrons towards itself, that oxygen coming in gave it the push that it needed. It steals those electrons and breaks away. What I get as a result, the carbon chain hasn't changed, but when oxygen came in, bromine was still attached. So bromine, facing forward on a wedge, got punched from behind. The oxygen couldn't come in from the front, so it came from behind, pushed the bromine out. And in the process, hydrogen also got pushed out of the way. So if the bromine was on a wedge in my reactant, the oxygen is now attached on dashes. This is considered a backside attack, where if I have a chiral starting molecule, which in this case I do, this is chiral and this is chiral, I get an inversion of stereochemistry, an inversion of configuration, where bromine forward results in an OH back. Bromine is now floating around somewhere in solution. It has those extra, we'll show them in light blue, 2 electrons, giving it a negative charge. It is happy, it is stable, it is uninterested in any kind of reaction. It's off in solution. And this right here is my final product. So a quick overview then of the substitution, the SN2 reaction. Substitution, we substituted the bromine for the OH group. Nucleophilic refers to the nucleophile, the molecule that did the attack. A nucleophile, let's quickly review terminology. Nucleophile comes from nucleo or nucleus and phile, which is loving. A nucleus is positive. Therefore, something that likes a positive is going to look for the positive. It is positive seeking. So we'll call it positive seeking. And what kind of molecule is going to go out of its way to look for a positive? Something that is negative or partially negative. In this case, we see the OH minus. It is a full negative -1. And the negative is attacking. So we have the substitution nucleophilic. Bimolecular tells us two molecules are reacting together at the same time. That is the incoming nucleophile and the alkyl halide. The alkyl halide refers to the chain. That's the alkyl group. The halide is the halogen, the leaving group sitting on the molecule. And our final product for an SN2 reaction is replacing the leaving group with a nucleophile, if chiral, with an inversion of configuration. Even though it is bimolecular, this is a one-step reaction, and it is a very fast reaction. This is really, really important to recognize. A fast reaction is because we have the OH minus, or whatever nucleophile is coming in, is strong. And that's the key to an SN2 reaction. SN2 has a strong nucleophile. How do I tell if something is a strong nucleophile rather than what we're going to see later, which would be a weak nucleophile? When you're thinking about strength in the context of molecules and atoms and electrons, think of what it means to be strong. For something strong, it will react. And that has us take a step back to something you've probably heard me say a million times, depending on how many videos you've seen. And that is, when something is happy, it is stable. And if it is stable, it is unreactive, which would make it weak. If something is unhappy, then it is unstable, and that makes it reactive. The idea here is that if a molecule is carrying a burden, what would make something unhappy? Something that has an incomplete octet, or in the case of nucleophiles, something that has a charge. Charge is a burden. The burden makes the molecule unhappy. And if it's unhappy and unstable, it wants to change its fate. It wants to become stable. And that means it's going to do an attack. That makes it reactive. The OH minus is unhappy. It has a burden of charge. It finds something it can attack. Boom, we get an attack. This is a quick reaction. We do not have time for a carbocation. If you take nothing else away from today's session, except for this, you will already be ahead. And that is absolutely no carbocation intermediate in an SN2 reaction. You cannot have a carbocation forming in a fast reaction because a carbocation is slow. The rate of an SN2 reaction is equal to some constant K times the concentration of the alkyl halide. We'll call it alkyl X, X being the halogen, and the concentration of the nucleophile, the incoming attacker. The constant is determined by the specific reaction. We don't care about that. The alkyl halide and the nucleophile, molecule 1, molecule 2, this is what makes the reaction bimolecular. This is the bi, and that's how we get the 2. Let me know if this finally makes sense, if this is finally clear about what the heck is going on with the SN2 reaction. And then I will give you some more information to hopefully help it be even more clear. We talked about the fact that this is a backside attack. I want to go into that in a little bit more detail so that you can very clearly see what's going on. Say I have a molecule like CH3Br, a very simple alkyl chain, and I want to draw it in 3 dimensions. So I have my carbon with my 3 hydrogens, which will draw like this. And remember, this molecule is trigonoplanar. I'm sorry, not trigonoplanar, tetrahedral, because it's an sp3 hybridized molecule. It's not quite drawn accurately, but let's say it's close enough. And here is my alpha carbon. This is my leaving group. If a nucleophile wants to come in and attack, and we can change up the nucleophile this time, we'll make it a CH3O minus. If it wants to come in from this end as an OCH3 minus, it can't reach the carbon. It's too blocked, it's too hindered, and it won't get there. So it has to swing around to the other side where there is an opening in the opposite side behind where that bromine is. And when the attack happens on this side, oxygen attacks carbon, bromine gets kicked out. And the way I think of this is, imagine that there is a bench and there are kids sitting on the bench. I used to use this example just in generic terms, but now I can totally see my kid doing that. He's like a little pushy kid. So we have a kid sitting on the bench, and my toddler comes along, and he doesn't want to sit here just because there's room. No. He needs to sit right there. So what he's going to do, if he can get away with it, is just come on over here and squeeze himself onto the bench or onto the chair. I'm telling you, this child can take any chair in the house. He wants to sit on mommy's chair, and he wants mommy scooch over. That's his new thing. Mommy scooch over. I want to sit here. And push this way. So where does this light blue one have to go? It gets pushed off. It's an opposite attack. If the kiddo attacks from the right, this one gets pushed over to the left. And yes, my 3-year-old can push me off the chair. Well, he tries to push me off the chair. Because of the way that this is happening. If there was a wall over here, then the kiddo can't come and attack and get onto the chair. So you have to look at the potential for hindrance on the molecule. And with regards to an SN2 reaction with steric hindrance, what we're looking at is if you have a methyl bound to a leaving group, like this one, there is absolutely no hindrance. This will be the easiest, fastest reaction because nothing's blocking it. Slightly more hindered than a methyl would be a primary alkyl halide. And that would be just, say, something that, we're running out of room here. Let's put this on the next page so we can draw some molecules. Let's move it down here. Okay, so for a primary alkyl halide, say I have something that looks like this with a bromine at the end. There is a big alkyl chain going on, but the nucleophile can still come in and attack from the side, making it accessible enough. Slightly less accessible, that is supposed to be a less than sign. Slightly less accessible, hold on, I have my signs backward, don't I? This is the easiest, and then this one, there we go. Slightly less accessible will be the secondary alkyl halide, which I've shown you in the last one, in the last example, where we use bromine on a secondary carbon. The nucleophile can still come and do a backside attack like that, but absolutely not happening is a tertiary alkyl halide. A tertiary alkyl halide will not undergo an SN2 reaction because it is way, way, way too hindered, and this is really important. No SN2 for a tertiary leaving group. That means if you're not sure what reaction takes place and you see tertiary, automatically rule out SN2, and you're good to go. The types of molecules that we're looking at to do an SN2 attack. We said that they have to be unhappy and unstable. So the SN2 nucleophile, what I'm looking at is typically something that is charged. For example, an OH minus, an SH minus, an NH2 minus. Notice that they all have a charge. Another thing I'm looking at, though, is something that is polarizable. If I can take a molecule that is relatively big, even if it's stable, if I can get all that charge to concentrate around one area, just all come in for that one big attack, then I can have an SN2 reaction, even if that molecule is, or atom is otherwise not very reactive. So for example, I can have a Cl minus, terrible base, good nucleophile, Br minus, I minus. These can make good or somewhat decent nucleophiles. Another class of polarizable is if I have resonance. So resonance falls under polarizable, but it is a unique case. So for example, if I have an acetate, acetate is very stable because I have a negative charge, or stable enough. I have a negative charge that is resonating over the 2 oxygen atoms. But if I look at the resonance hybrid, that is the in-between of the 2 resonance structures. And I have my partial negative here and my partial negative here. But I bring something very partially positive nearby, like this carbon. If I have this next to a resonating molecule, then all the negativity will now come down towards this oxygen so it can concentrate and attack. And common ones that you're going to see are this right here and N3 minus. The azide anion is another one that you want to look out for. If you are just joining in, welcome. We are covering an introduction to SN1, SN2, E1, and E2 reactions. Do not worry about taking the notes. I am taking them for you. Just comment live notes and I will send you a link. Yes, even if you're watching the recording, just comment live notes and I will send you the link. So with regards to the molecules here, we have a question. They are not strong bases, they are strong nucleophiles because the attacker in an SN2 reaction is called a nucleophile. The attacker in an elimination reaction is called a base, so we'll get to that after. So this right here does not make a good base. It's a good nucleophile. Not a good base is a good nucleophile. Well, that would be a good base and a good nucleophile, but we'll get to that later. All right, so we have our strong molecules. You're looking out for the negative charge. You're looking out for resonance. You're looking out for the ability to polarize. And we already talked about the fact that there will be absolutely no carbocation. So let me just give you a quick overview of what you're looking at. It's a bimolecular reaction. That means we are looking for, well, first of all, it is fast. That means we have a strong nucleophile that will do the attack quickly. It's not going to hang around. Absolutely no carbocation and no tertiary leaving group. Carbocation would be too slow. Tertiary leaving group would be too hindered. Bimolecular means that it is one step. And if there is chirality, there will be an inversion of stereochemistry. All right, that wraps up the SN2 reaction. I see we have a couple more latecomers. Welcome. If you're with me so far, go ahead and give this video a thumbs up. If you're not subscribed to my channel yet, what are you waiting for? I'm hoping to reach 1 million subscribers. One video, one live stream at a time, but I need your help. Please, please go ahead and subscribe if you haven't yet. And let's move on to the other strong reaction, which is E2. The E2 reaction should really be a beta E2 because we're specifically looking at a, I don't know why I wrote the beta with a beta. We're looking at a beta. E stands for elimination. And once again, the 2 does not tell me how many steps, but instead it tells me that it is a bimolecular reaction, which by now you should know means 1 step, 2 molecules reacting at the same time. And when you hear that, now you should recognize 1 step means a strong, fast reaction. Let's take a look at the same exact starting molecule we had before, where I have something like bromine as a leaving group. But let's categorize this molecule a little more because we have more going on in this case. I do need to remember that we have students watching on mobile, so I'm going to try to draw bigger. If I forget, please remind me, because I see that, I hear that more and more students are on their cell phones. I want to make sure you can still see everything clearly. The molecule we're looking at has the leaving group sitting at the alpha position. Wherever that leaving group is, that is considered the alpha carbon. The carbon next to it is the beta carbon. So in this case, we have 2 different beta carbons, one on the right, one on the left. They are not the same, but sometimes we can have them be the same. Alpha, beta, gamma, we don't care about gamma. It's just alpha and beta. And specifically what I'm looking at on the beta carbon are the beta hydrogens. On the right, I have 2 beta hydrogens, which I marked in green. On the left, I have 3 beta hydrogens, which I will mark in light blue. These are very, very important, so we'll come back to that. I have my alpha and my beta. What happens in this reaction, first of all, just like last time, the bromine is pulling on the electrons between itself and carbon, making it very partially negative, and the alpha carbon very partially positive. But, and this is where the elimination reaction is different, instead of getting attacked directly, when the molecule is still as is, before it gets attacked, when bromine pulls on negativity between itself and carbon, carbon becomes partially positive, which we already discussed. But what will happen is other atoms nearby are going to be pulled into this. This has become a big family drama, and all the electrons are getting pulled. In the case of the hydrogens, these electrons are also having some of their electron densities pulled in, and that makes them ever so slightly partially positive. And that means when I have a strong base, in this case, beta elimination happens with a base. If I have a strong base nearby, and oh my goodness, we have the same OH minus again. Yes, it can be a nucleophile and a base. The classification has to do with the context of the reaction rather than the type of molecule that it is. So the OH minus has an option to attack right there. That makes it a nucleophile. But if instead of attacking at the alpha carbon, it chooses to grab a hydrogen from the beta position. If it grabs the hydrogen, hydrogen can only have one bond. And so the electrons that are already kind of being pulled will now break away towards the alpha carbon, which would put too many bonds on the alpha carbon and therefore kick out the leaving group. So in a one-step bimolecular reaction, the OH grabs the hydrogen, the electrons collapse towards the alpha carbon, the bromine, the leaving group gets kicked out. And what we're left with now is a molecule that looks like this. We have our carbon chain. The hydrogen, there used to be 2 hydrogens here. Now there's only 1. There is also a pi bond sitting between the former alpha and former beta carbon, like this. And somewhere off in solution, I have my OH, which is no longer an OH minus because it has that extra hydrogen. Now only 2 lone pairs, no charge, and it's gone, never to be heard from again. And this is my final product. We don't show hydrogen, so I'm just going to leave it clean like that. This is the product of an elimination where we have, this is one of the products of elimination, where we get the pi bond forming. A couple of things to note here. What made the OH minus act as a base here rather than a nucleophile? So let's go back really quick and talk about one more thing that I forgot to mention. An SN2 reaction, what we looked at before, prefers a polar aprotic solvent. An aprotic solvent is one that does not have hydrogen bonding. And when the solvent is not capable of hydrogen bonding, meaning we don't have an OH or an NH. OH, think of water, alcohol, NH, think of amines, ammonia. Then the solvent will not stabilize or interact with the base, forcing the molecule to act as a nucleophile. In the case of the elimination reaction, so let me show you what the actual reagents are. In the last reaction, we used NaOH, but we'll use DMSO, which is one of the most common polar aprotic solvents that you have to memorize. In this case, if I use the same NaOH, but I put it into a protic solvent, and here's a trick, it'll typically, well, a hint, not a trick, it'll typically be its own conjugate solvent. So what is the conjugate acid of OH minus? H2O. That right there is a polar protic solvent. It is capable of hydrogen bonding, and it will make the attacker act like a base rather than a nucleophile, even if it can be the same thing. So we have our alkene that formed, but that is not the only alkene that could have formed, because this right here is a transalkene. Let's hold that thought. What if the OH minus instead chose to attack at the other beta position and grab a blue hydrogen. That would put the pi bond right there, which absolutely can happen because that would give me a product that looks like this. This right here is a terminal. We don't need the word terminal. You recognize that? That is another option, but that is still not the only option because our starting molecule, I'm going to redraw it here, looked like this. The carbon here, sp3. The carbon here, sp3. That means the molecule is capable of free rotation, and at any point in time, it could have rotated to look something like this. And in this case, we have two hydrogens, so it actually doesn't matter because depending on which one I grabbed, it could have turned and given me a product. This is kind of a mess all over the place, but it also could have given me a product that looked like this. So first, let me know yes or no in the comments if you see how I was able to get 1, 2, and 3 products for this E2 reaction. And while you type that in, I'm going to show you a quick rundown of stability. If I have a carbon-to-carbon double bond with nothing else on it, just hydrogen atoms, this right here is not substituted. When it comes to a pi bond, the more substituents I have, the more carbons I have on that pi bond, the more stable that pi bond will be. And so this one right here is not substituted, therefore it is the least stable of all the potential alkenes that I can have. Slightly more stable is if I have a pi bond with one substituent. This one is called a monosubstituted pi bond because it only has one substituent. A trick for this, the highlighter trick, is this. Highlight your pi bond so you can see exactly where it is, and then draw an arrow to every single carbon that comes out of that highlighted portion. I have one monosubstituted. But if I take that pi bond now and I put it here, or I put it here, or I can also have something like this. From stability, hang on, let me just organize them by the appropriate stability. Least stable at the top, most stable at the bottom, within the fact that these are all di-substituted. If I highlight each of the pi bonds, 1, 2, 1, 2, 1, 2, these are all di-substituted, but this one is the least stable because the two groups are very close together. This one is the most stable because the two groups are farthest apart. These are di-substituted. If I add a third group onto it, this right here, watch, highlight, and 1, 2, 3, tri-substituted. And last but not least, the absolute highest degree of substitution I can get on an alkene. If I highlight the pi bonds, I have 1, 2, 3, 4. This is tetra-substituted, the most substituted, and therefore the most stable. Let me know if you see the highlighter trick saving you time. Let me see fire emojis in the comments because you will never be confused with substitution on this again. I see a couple of questions, so let me go back before we continue. Can you define protic and aprotic again? Yes. Let's go back to wherever I put it, right there. Aprotic, A means without, protic is the proton capable of hydrogen bonding. So the question for you is, do you like to have fun? Because hydrogen absolutely likes to have fun, FON. There is no fluorine in your solvents that you're going to see, but we are going to look at oxygen and nitrogen. If hydrogen is having fun because it is attached to an oxygen and nitrogen, the electronegativity difference is so extreme compared to anything else that you're going to have such polarity, the solvent will be very, very attracted to the next one and the next one and the next one. So let me show you what I mean. If I have a water molecule, Hydrogen is most definitely having fun. It's attached to an oxygen. The polarity here makes for a very partially negative oxygen and very partially positive hydrogen. If I bring another water molecule nearby, this partially positive hydrogen is now so attracted that the best way to describe how strong this bond is to ask you if you have ever belly flopped into a swimming pool. And if you haven't, just fill your sink with water and slap it. It's water. Your hand should go through, but it kind of hurts. When I was learning how to dive, a lot of belly flopping. Trust me, that pain that you feel, the water smacking you back, that's a hydrogen bond. That right there is a polar aprotic solvent. But if we're looking at a polar, I'm sorry, this right here is a polar protic. A means without. So this right here is protic because it most definitely has a hydrogen bond. Aprotic would be something like DMSO, which you do have to memorize if you're taking an exam like the ACS. DMSO stands for dimethyl sulfoxide. So it's a sulfonyl, sulfur, and oxygen double bound with 2 methyl groups. There is a bond between sulfur and oxygen, but there's no hydrogen. Hydrogen is only on carbon, and carbon to hydrogen is not polar. Therefore, there is no capability of hydrogen bonding. Aprotic solvent. Very good question. Let me know if that's clear. Can we say the base and nucleophile thing again? Okay, so here's the thing about a base versus a nucleophile, because I get that question a lot. A lot of students get confused with what's the difference between a base and a nucleophile. So let me see a scared emoji in the comments if that's been bothering you, followed by a clapping emoji if you never want to worry about that question again. Okay, so we're going to look at a nucleophile versus base. If I give you an OH minus and I ask you, is it a nucleophile or a base? It's kind of a trick question because I already said it can be both a nucleophile and a base. And so really the question is, what makes a nucleophile? What makes a base? If I have a molecule that gets attacked, we'll use the same molecule because that's the one we did before. If it gets attacked directly at the alpha carbon and the leaving group kicked out or carbocation for SN1, this is acting as a nucleophile. And the idea here is the nucleophile is attracted to that partially positive carbon. But if my attacker does not attack the nucleophile, instead it grabs the beta hydrogen to kick out the leaving group or a beta hydrogen next to a carbocation, now it is acting as a base. So the difference is simply the context of the situation. And the example I like to use is, I was talking about my kiddo before and how my husband's going to take care of him so that I can continue teaching. To my husband, I am a wife. To my son, I am a mother. Am I a mother or am I a wife? Well, actually, I'm both. It depends on the context of the situation. And if you're referring to my son, I'm a mother. My husband, I'm a wife. I can be both. So the molecule here can be both. It just depends on the situation. Some molecules will be only nucleophiles. Some will be only bases. But really, you're looking at how it reacts and how it attacks. So very good question. Let me know if that makes sense. The base is something that grabs a hydrogen. The nucleophile is the one that attacks the alpha carbon. That is the difference between them. Will it choose the more substitute? We're going to go back to that. That's a really good question, and I'm definitely not done explaining that. So let's keep this on here for a moment. Yes, I'm going to explain all of them again because I see a couple of questions. Brian, better late than never. It is good to see you. Why fluorine is weak in polyprotic solvent? So fluorine is such a tiny, tiny, tiny atom that when fluoride is attached, it does not want to let go. It does not play nice, and that's why we don't see it in most of the reactions. Also DMF, yeah. The 5 that you have to memorize are DMSO, DMF, acetonitrile, ethers, or the THF is specifically one, and acetone. Those are the 5 that most commonly come up. So absolutely make sure that you memorize them if you are required to. You said no hydrogen bonding, but in the SN2 reaction, we use NaOH that has a hydrogen. No, Taylor, you're not overthinking. That is a very, very, very good question. So let's come back to it. OH minus is not going to waste its time with hydrogen bonding because it's negative. It will attack the entire hydrogen and just pluck it off. We're talking about a solvent that is neutral, floating around in the millions. So 1 OH minus in a solution of water is a strong attacker. But what about the water? The water, the solvent, that's what we're looking at for determining between SN2 and E2. That's a really, really good question. I love that you're thinking like you're trying to put the pieces together. So hopefully that makes sense. Can you write them out? Yes, I can. Let's put them here. So these are the 5 common polar. They're all polar, but they are aprotic solvents. If you are taking an exam like the ACS, let me know in the comments if you are. You have to memorize and know what they look like. DMSO, DMF, acetonitrile, ether, and the one that I had to memorize in class was THF, tetrahydrofuran, and I keep forgetting, acetone is just a ketone, but it's a small one, so it's often used as the solvent. So these are the 5 that you should memorize for the SN2 reactions. All right, so let's go back to here. Now that we know the stability, when it comes to choosing which one is the major product, remember happy, stable, unreactive. Happy and stable also means it is likely to form, more likely to form, and faster to form. So the more substituted your product, the more likely it will form. And if we have a choice between multiple products, in this case, we had 1, 2, and 3, 2 disubstituted, 1 mono, the more stable is going to be the major product. This is a mess. Give me a moment. Let's clean this up a little bit so that you can follow along, especially when you're reviewing the notes. So I'm going to write the 3 products again over here. So we had our first product that I drew. I'm going to draw it on a different color so you know that I'm doing a redraw here, was a trans alkene that is disubstituted. The second one that I drew, or no, that was actually the third one that I drew. The second one that I drew was a monosubstituted. And the second one here was a cis disubstituted. The one over here is the major product because it's the most stable. This is the minor product because it is the least stable. And this one is in the middle. Trans is more stable than cis, which is more stable than the monosubstituted. These are the 3 products based on the different hydrogens that I grabbed. But what if you don't have the time or patience, most of the time, on your exam to draw the mechanism? Put shortcut in the comments because I feel like I haven't shown you any shortcuts yet today. So let's take a look at some shortcuts for coming up with these reactions or with these products. Actually, let's backtrack. I forgot to show you the SN2 shortcut as well. So let's just put shortcuts right here. If I have a molecule that is to undergo an SN2 reaction, for example, something like this, reacting with, let's go with NaNH2 in DMF. I'm totally making things up here, but you could see this on your exam. What do I have here? I have a leaving group sitting on an easily accessible primary carbon. I have a strong, unhappy attacker because Na plus is a positive spectator. NH2 minus is a strong attacker. We have a polar aprotic solvent, which tells me that I'm likely looking at SN2 over E2. I'm not going to draw the whole mechanism. You identify your alpha carbon. The leaving group is on it. You don't draw the leaving group. You just draw everything else for the product. Carbon skeleton as you see it. And then, you know what? Let's change this up a little bit. Let's make it look like this and chlorine, because we already saw bromine. The reason I changed it this way is because now my leaving group is on a chiral carbon, and the shortcut, you redraw the carbon skeleton exactly as you see it, except for the leaving group. Because the leaving group is on a chiral carbon on a wedge, for my product, I'm going to draw dashes, and then I just put that on there. If I was given this in reverse and told to come up with a starting molecule, or say it was drawn like this on your exam, where you had to fill in this piece right here. Here's what you do. You identify your molecule, you cut off your nucleophile, and you just put a leaving group right there. No nucleophile, put a leaving group right there. And that is the shortcut for SN2. That one, not so important. SN2 was not hard. But do you want to see the shortcut for E2? Especially when we have the option for so many products, and let's say you're asked to only draw the major product. How do you know which one? Why am I drawing the same molecule? Let's draw something more complicated. Let's put a ring, and then a couple more carbons here, and then we'll put a chlorine right there. How's that? We're going to react this one with NaOCH3. That is really just Na plus positive spectator. CH3 is an OCH3 minus. Its conjugate solvent, CH3OH. Recognize that this is a polar protic solvent, more likely to do E2. Here's what we're going to do to come up with a product. Identify the alpha carbon, identify the beta carbon. This beta carbon here has 3 hydrogens. It is a primary beta carbon, therefore the hydrogens are also primary. They're primary hydrogens. This one here is a secondary beta. That means it has secondary beta hydrogens. Now here's the trick. The pi bond will either go here between the secondary and the alpha, or here between the primary and the alpha. Anytime it's secondary, you want to look for cis and trans. So the moment you see secondary, look for cis and trans. That gives us 2 products. That right there is a 3rd product. And then if you want to know which one would be the most substituted, the trick is very simple. The more substituted the beta carbon, the more substituted the beta hydrogen, the more substituted the resulting pi bond. So I know without drawing a single product that the most stable major product will be the trans version of the most substituted one getting eliminated. And that's the one I would draw if I'm asked for the major. So let's see. This is going to be a mess. So I'm just going to draw this right here. So the first one I'm going to draw is my carbon skeleton exactly as I see it, with 1, 2, 3, 4 carbons coming off of the benzene ring. 1, 2, 3, 4. A pi bond between the secondary beta and the alpha. And I know already that this is my most substituted, but hold that thought. Let's draw it again. And this time I want to flip that last carbon to cis. 1, 2, 3, 4. And there's a pi bond. I don't know why that one got kind of stuck out there. So there's another one. And for the last one, I'm going to draw the 4 carbons, 1, 2, 3, 4, but put a pi bond between the alpha and the less substituted. So I did draw them all, but I told you before drawing anything that this is most stable. And the trick is the trans version of the most substituted carbon. And look at that. If I do the highlighter trick on all of them, I highlight the pi bond. 1, 2. This is disubstituted trans. 1, 2. Disubstituted cis. And just 1. This is monosubstituted, no cis or trans because it's terminal. And that means this one is my major product and this one is my minor. Now, I didn't name them before, but Mr. Hoffman is the one who came up with this rule that, hey, we got to look for the most stable one. So this is called the Hoffman product. I always spell his name wrong. I think it's 2 N's. Let me look that up. Yeah, I think it's 2 N's. The Hoffman product simply means the most substituted. And on the rare occasion where you have an exception, that is, well, I'm sorry, not the Hoffman product. The Hoffman product is the tricky one. The Zaitsev product. Zaitsev is the most substituted. This would be the Hoffman product, but not something we form with a typical regular small base. All right, couple of questions first. Is it minor because it's monosubstituted? Yes, because it's monosubstituted, it is least stable. And if it's least stable, it's least likely to form. This one is most stable, which makes it most likely to form. Why does also using heat proceed to elimination? I get confused. That is a very, very, very good question. We totally don't have time for this, but sure, why not? Let's talk about it. If I look at a molecule that can potentially undergo SN2 or E2. I don't know the exact energy diagram for this, so I'm going to be making it up. The relative heights can change, but the concept is the same. So we'll say that this molecule starts out at this level, kind of sort of stable, and we're looking at the energy diagram here. So this right here is a measure of energy. If I have this molecule undergo an SN2 reaction, then we have an activation energy and we have a product. Product for the SN2 reaction is going to be some kind of nucleophile here. If, on the other hand, this molecule undergoes an E2 reaction, it's a higher activation energy, but a lower energy product. So bear with me. This is the activation energy, and this is the activation energy. The resulting product between SN2 or E2, they're both more stable than the starting molecule, but the SN2 has higher energy. It is less stable. The lower the energy, the more stable. The E2 is a lot more stable. So why wouldn't they all go to E2? Well, the energy investment, it costs so much more to get the better product. So let me know if that's the case for you. You want to buy something, the thing costs that much money, you're like, yeah, I'm just going to go on Amazon and get a knockoff. My son loves magnet tiles. And so he got a set for his second birthday, kind of into it. For his third birthday, he got a set and he's obsessed. So we went to the internet store. That's what we tell him, where we buy everything. We go on Amazon, we call it the internet store, and we got him a massive, massive set of magnet tiles so that he can build villages and towers, and that kid likes magnet tiles. The actual magnet tile brand name is like $100 and something. I'm not buying my 3-year-old a toy that's $100 and something for him to break. I got a knockoff for like 20 something bucks, same exact thing. And yeah, it's going to break faster. It's not like he cares. And so this is kind of the shortcut, right? You pay less, you get the knockoff, and you know, you get what you want. My son is happy. He doesn't know the difference. But it's going to break faster. I'm probably going to have to replace it faster, whatever. If I really, really wanted to, because some things that I buy for him, like his, I don't know, certain things that I don't want cheap crap because, I don't know, bath toys or something. I don't want lead or other chemicals in it. I will spend more money and get a much better quality thing. And so the question is the investment that gets you there. When we're talking about energy, how do you put more energy? How do you raise the activation energy that you're putting into a system? Heat. And so if you put heat into that reaction, you're helping it go all the way up so that your resulting product is so much more worth it, but you're spending $100 on magnet tiles to get the good stuff. Now I shouldn't really be going into it, but I'll give you a quick overview. The idea is that to make a pi bond costs a lot more energy because you have to perfectly line up the orbitals so that the electrons can collapse. That's where you need the heat. But the reason this is more stable, it has less entropy because everything is locked into place, where here it's a tetrahedron. It's got an sp3 carbon. Things are still moving around. They're still flailing. It's not as stable. So not something I had planned to explain, but if this makes sense, if this is something you've been wondering about, let me know in the comments because I think it does help to understand the why behind it. Why is it SN2 when it's a secondary carbon? It's not about the carbon, it's about the attacker. So secondary can undergo SN1, SN2, E1, and E2. How do we identify which is the nucleophile and solvent and how, ask me that question in the SN1 reaction. That's a really, really good question. Hold that thought. I want to come back to it. Okay, let's hold that thought. Is trans always stable? Yes, trans is more stable. Heat is not always there, but it absolutely helps. The middle product will not be formed as the removal of a proton follows into, let's see. So this one right here, we have two hydrogens, 1 and 2, one going forward, one going back. And so when the molecule rotates, it will be lined up in the right plane. And in this case, it can happen, yes. Excellent. All right, we got quite sidetracked. We're at the top of the hour. Quick vote. Continue and talk about 2 more reactions, SN1 and E1, or call it a day because it's been an hour. Regardless of how we continue, completely forgot to mention this before. We're covering the basics today, but the real way to learn is practice, practice, practice. And that's why I am very excited to tell you that I have a midterm practice worksheet that I created just for you. It is not available on my website. Just put midterm in the comments and I will link you so you can download it and do quite a few pages worth of substitution elimination practice. Reactions, fill in the reactions, choosing between reactions, all the good stuff. All right, so let's continue. We talked shortcuts, we talked Zaitsev. Let's do an E2 summary because I got a little sidetracked and I want to make sure we kind of wrap it up before we continue. And so I'm trying to think of what to go into and what not to go. I could talk about substitution elimination for hours, but no time right now. The rate of an E2 reaction is some constant K times the concentration of the alkyl halide, which I'll call alkyl X, and the base. Once again, having 2 things reacting at the same time is how we get the bimolecular, 1 step, 2 molecules at the same time. That means we have to look out for the fact that this is a fast reaction because we have a strong base reacting. There is absolutely no carbocation in an E2 because it is 1 step. 1 step does not allow time for a carbocation. Zaitsev's rule is the one that we will follow unless we have a big bulky base that is simply too bulky to grab. And the trick is you want to grab the most substituted hydrogen. And unlike SN2, primary, secondary, and tertiary are all possible in terms of the substitution of the leaving group. So we're not ruling any out like we did with SN2. We're not going to go into that because we don't, you know what, we are going to go into it. I'll do this really, really quick. A big bulky base is the exception to Zaitsev's rule. And that is because a big bulky base, which I call the triple B, is so big that it's going to be sterically hindered. Even something as simple as this molecule right here. To get to these hydrogens when it is so big and bulky is very difficult. And even though it would love to grab that light blue hydrogen, it can't. So it will settle for the next best thing and grab, I'll show it over here. Color I'm going to use with Mr. Purple. We'll grab from the end. So we grab it off the end. This will give me the Hofmann product. And the Hofmann product, that is the less stable pi bond. But don't think of it as a less stable pi bond. Think of it as I can either grab the, words are failing me. I can either grab the less substituted hydrogen or grab nothing. So I'm going to choose the less substituted hydrogen over the nothing because, you know, if that's the only option, that's the option I'm going for. The big bulky base in question, for Orgo 1 students, you probably just learned tert butoxide. Orgo 2, you probably also covered LDA. We'll look at tert butoxide specifically. Tert butoxide, tert butyl oxide, written in a million different ways. The most confusing one for students is KOTB, so let's talk about that one. K plus is simply a positive spectator, just like Na plus. OTB is O, tert butyl. That is it. It's a carbon with 3 methyl groups and an O minus. But if you draw it out, you'll realize the carbon has 3 carbons and each one has 3 hydrogens. And that makes it really, really big and really, really bulky. That's why it will go for the less substituted hydrogen, even though that is not the ideal product. It doesn't have a choice. You know what? Given the time and that I have jury duty tomorrow, let's do this. Let's make this part 1, and let's continue next week with a live stream as part 2. So this is part 1, the SN2 and E2 reaction. In part 2, we'll dig into just as much detail for SN1 and E1. Don't forget to comment live notes for a copy of everything from today and from part 2. Comment midterm for the SN1, SN2, E1, E2 midterm practice worksheet.